Hey there, Mr. Sutton here with the Pre-Cal Honors 4-6 Extra Practice Number 1 solutions on exponential equations. To solve this exponential equation, it looks like we've already got the exponential term isolated, so we're just going to take the log of both sides. Now, in terms of logs, we're going to use ln on both sides because ln is the log base e. So if I take the ln of the left side, that's going to pop out the 6x, and the ln of e next to it is just 1, so we really just have 6x. On the right side, we're going to have ln of 3. And now all I have to do is just divide both sides by 6. So x is going to be ln of 3 over 6, which I will now calculate on the calculator. So dividing this out on the calculator, rounding to 2 decimals, that's going to come out to about 0.18. On this problem, I noticed that 64, 32, and 1 over 2 are all powers of 2, so I can use the common base method if I want on this one instead of using logarithms. So let me express all of these as a power of 2. 64 is really 2 to the 6, and I still have that negative x outside there. 32 is 2 to the 5th, and then I can express 1 over 2 as 2 to the negative 1. All right, let me combine things using some exponent rules here. First, let me turn this into 2 to the negative 6x, because we're multiplying these exponents together if we're raising one power to another. And then I can combine these 2's on the left side, which are being multiplied by adding the exponents. So this is really negative 6x plus 5. And then now that I've got just 2 to something on one side and 2 to something on the other side, I can cancel out the bases and set the exponents equal to each other. So this is going to be 5 minus 6x equals negative 1. Subtracting 5 from both sides, I have negative 6 over there. And dividing by negative 6, I end up with x equals 1. For this problem, I noticed that 1 over 625 and 25 both have a common base. These are both powers of 5. In fact, they're actually both powers of 25. So I could actually, if I'm using the common base method, I could leave this 25 to the negative 2v the way it is. But this 1 over 625, I can really express this as 25 to the negative 2 power. And now just using some exponent rules here, 25 to the negative 2 to the negative v, I'm multiplying those exponents together. So this is really 25 to the positive 2v that I have on the left side. Canceling out my common bases, I can write this as 25, or 2v rather, equals negative 2v. Adding 2v to the other side here, we have 4v equals 0, so then v equals 0. For this problem, trying to solve this exponential equation, I noticed that 8 and 2 are both powers of 2, so let me just use common base method on this one instead of logarithms. I'm going to rewrite 8 as 2 to the 3rd power, and then raising 2 to the 3rd to the x minus 1, I'm multiplying the exponents. So we have 3x minus 3 for that exponent. Now that I have 2 to the something equals 2 to the something, I can cancel out those 2's and just write 3x minus 3 equals x plus 1. So then adding 1 to one side and subtracting x to the other side, I can write 2x equals 4, so then x equals 2. For this problem, 3 and 12 are not both powers of an easy base anyway, so I can't use common base method here. I'm going to have to use logarithms. I noticed that this 3 to the x term is already isolated, so I can just go ahead and take the log of both sides. So on the left side, my pop-out rule gives me x log 3, and then I'm going to have equals log of 12 on the right side. Now I just have to solve for x. To do that, I'll just divide both sides by log of 3. So I have log of 12 over log of 3, which I can now figure out on the calculator. So plugging this in, and to get the fancy fraction, I did alpha y equals. So this is going to end up being, let's see here, about 2.26 if I round it off to 2 decimals. To solve this exponential equation, I take a look at my bases first to see if I can use common base method. And I see that 4 and 64 are both powers of the same base. They are both powers of 4, also 2, but I mean 4 is easier to work with. So I can just leave 4 to the 2x plus 1 the way it is. 64, though, I can express that as 4 to the 3rd. And then let's see here. We've got 4 to something equals 4 to something else. Let me just cancel those 4's and write 2x plus 1 equals 3, just setting the exponents equal to each other. So then we've got subtract 1 from both sides. That's 2. Divide by 2, you've got x equals 1. And we're done with this one. For this problem, there's a few ways to go about this. We could cube both sides and then go from there. I'm just going to immediately turn the left side into an exponent so I can use logarithms. So I'm going to rewrite this as 6 to the x over 3 using that fractional exponent setup. And now I'm just going to take the log of both sides with my pop-out rule. That's going to give me x over 3 log of 6 on the left side and log of 50 on the right side. And then if let's see here, I've got to multiply 3 by both sides, divide by log of 6. So I'm going to end up with 3 log of 50 over log of 6, which I can now do on the calculator. And let's see what this comes out to. About 6.55. On this problem, to solve this equation, let me start by isolating the exponential term. So I'll subtract 9 from both sides to get negative 2, and then divide by negative 4 to get positive 1 over 2 on the right side. Now to get rid of e to the v, I'm going to take the log of both sides, but since this is e, I'm going to use ln on both sides because ln and e cancel out. So this is actually just going to leave me with v on the left side and ln of 1/2 on the right side, which I can now plug into my calculator. So plugging that in, I end up with about negative 0.69 for that answer.